NoPath addresses a fundamental challenge with large language models. They're powerful, but prone to hallucinations when answering factual questions. This framework cleverly leverages the LLM's own internal knowledge to guide how it explores external knowledge graphs. It creates a collaboration between the model's parameters and structured external data. The result is more accurate answers with clear reasoning paths that show how the system reached its conclusions. Testing shows it outperforms previous approaches. Figure 1 illustrates the key problem. When asked, what language is spoken in Netherlands and Belgium? An LLM alone might hallucinate North Germanic. The middle approach using knowledge graphs doesn't provide enough context for good reasoning. NoPath's innovation is mining the LLM's internal knowledge first, using that to guide how it explores the knowledge graph. This two-step process creates better integration between what the model knows and what's in the external database, leading to more accurate and interpretable results. Figure 2 shows NoPath's workflow through a practical example. It starts by generating inference paths from the LLM's internal knowledge. These paths guide the exploration of the knowledge graph, dynamically building relevant subgraphs at increasing depths. The system evaluates at each stage whether it has sufficient information to answer. The visual example shows how it handles the question about Whistler Mountain and Demi Lovato's tour, creating a directed reasoning path through relevant information, maintaining clarity in its decision process. Section 2. Details. NoPath's methodology. The system first extracts the LLM's internal knowledge about topic entities using prompts. It then explores the knowledge graph at increasing depths, with the LLM selecting the most relevant relationships and entities at each step. This creates directed paths that show the reasoning process. What's unique is the bidirectional flow. Internal knowledge guides external exploration, and external knowledge enhances the final answer. If the graph exploration doesn't yield an answer, it falls back on the LLM's internal knowledge paths. The experimental setup in Section 3 rigorously evaluates NoPath against diverse baselines. The 4 datasets represent varying complexity, from simple factual queries to multi-hop questions requiring complex reasoning. The comparison includes LLM-only approaches, methods that fine-tune LLMs with knowledge graph data, and other prompting-based methods that combine LLMs with knowledge graphs. Freebase provides the structured knowledge, and they limited exploration depth to 3 for practical efficiency. This comprehensive evaluation framework enables fair comparison across methods. Section 4 presents impressive results. NoPath outperforms all other prompting-based methods across all datasets. The improvement is especially notable on complex multi-hop reasoning tasks like CWQ, where it achieves a 5.2% gain. Beyond accuracy, it's remarkably efficient, using 55% fewer LLM calls and 75% fewer tokens than competitors. The ablation studies show both components matter. Removing either the inference paths generation or subgraph exploration significantly hurts performance, confirming the value of the dual knowledge approach. The case studies in Section 4.5 demonstrate NoPath's advantages in real scenarios. In the CWQ example about Zhangjue and sacred texts, competing methods fail to find enough context and incorrectly answer typing Jing. NoPath succeeds by first generating inference paths that identify the Taoist connection, then exploring the knowledge graph to find the sacred texts. Similarly, in the web questions example about League Cup winners, NoPath accurately identifies Liverpool FC, while other methods fail or give incorrect answers. The visualization shows the clear reasoning paths. NoPath represents an important advance in making LLMs more factually reliable. By leveraging the complementary strengths of internal model knowledge and external structured data, it creates a system greater than the sum of its parts. The directed subgraphs provide clear reasoning paths that users can follow and trust. Beyond the impressive accuracy improvements, the significant reduction in computational resources, 55% fewer LLM calls, 75% fewer tokens, makes this approach more practical for real-world deployment. This framework has promising applications wherever factual accuracy is critical.